In the previous lecture, we started with the binary search trees, and also we have gone through the topics such as inserting the element into the binary search tree, removing an element from the binary search tree. We'll see by recapping the last lecture, we'll see some more concepts that are related to the binary search tree. Binary search tree is a binary tree, just like a normal tree, and we can say binary tree is an extension of general tree with a condition that the tree must consisting of 0 or at most 2 children. That means every node in the tree must have at least minimum 0 or mostly 2 children. That is what we call binary tree. Binary search tree is also a binary tree, but with the condition that in binary search tree, all nodes in the left subtree have values less than that of the root node. Correspondingly, all nodes in the right subtree have a value either equal to or greater than the root node. This is what the condition. That means for every node in the tree, left hand side value must be lower than the corresponding node, the parent node, and right hand side of the parent should consisting of the greater values than the parent value. This is what the condition that need to be applied on the binary search tree. This condition must be satisfied for insertion and deletion operations. Correspondingly, all nodes in the right subtree have the value either or equal to greater than that is equal to or greater than root node. So this is just now I discussed it. The same rule is applicable for every subtree in the tree. Due to its efficiency in searching elements, binary search trees are widely used in dictionary problems. The reason is whenever you know a value, just directly you compare with the root, and if the value is if the value is less than root, obviously here we are automatically eliminating the half of the tree and going to the left side. And the recursively the searching operation will be done at the left side so that the element will be found. So that is the reason it is best used in the dictionary problems. The binary search tree will look like this. In this, we have seen in the last lecture 39, 27, 18, 9, 21. See, you look at whatever the elements that are at the left hand side of the root are less than the root value. You look at 9, 10, 21, 19, 21, 18, 27, 29, 28, 36. All these values are less than 39. Where in case of right hand side values, or we can say right subtree, the values that are available in the right subtree are greater than the root value. This is true for every node in the tree. If you look at the 27, the left hand side values, that is left subtree values, are less than 27 and right subtree values are greater than 27. In the same way, we have seen in the last lecture how to create the binary search tree. The binary search tree, for example, these are the elements that are to be listed to be inserted into the binary search tree. First, we'll consider the first element and we'll make it as a root node. And the next element will be compared with the root value. If it is less than root value, then it will be placed at the left hand side of the root. Otherwise, it will be placed at the right hand side of the root. Next element, what you got is 56. 56 is compared with 45. So 56 is greater than 45. So that reason we are going to place it at the right hand side. So the next element is 12. Now the 12 is compared with 45. Since 12 is less than 45, we should move it to the left hand side. Now in the left hand side, we find the node called 39. but 12 is less than 39, so we have to place it at the left hand side of the 39. So this is the way you are supposed to insert. Next element that is to be inserted into the binary search tree is 34. So 34 is compared with 45. It is less than 45, so we have to move into the left hand side. Then 39, 34 is less than 39, so we have to move at the left hand side. And the 12 is the value which is less than 34, so that means 34 is greater than 12, so it must be placed at the right hand side of the 12. The same to be continued for the rest of the tree. So finally the tree will be formed like this for the given list of elements. Next, how to search a value in the binary search tree. The searching of the value is same like insertion. First, we always compare with the root. Then we have to decide whether to move into the left hand side, left direction, or in the right direction. The search function is used to find whether a given value is present in the tree or not. The function first checks the binary search tree is empty or not. If the binary search tree is empty, then return the null. Otherwise, what it has to do is, otherwise, if it is, then the value we are searching for is not present in the tree, and the algorithm terminates by displaying the appropriate message that a tree is empty. However, if there are nodes in the tree, then the search function checks to see if the key value of the current node is equal to the value to be searched. If it is, if the value to be searched is the root value, then we are very happy there itself we will find the answer. Otherwise, if not, it checks if the value to be searched for this is less than the value of the node in which case, it should be recursively called on the left child node. That means if the searching value is less than the root value, then we need to move into the left hand side, and recursively we need to perform the same operation at the left side so that we will find the element. In case the value is greater than the value of the node, it should be recursively called where it should be recursively called at the right hand side. That means we have to traverse to the right subtree. So this is the pseudocode that was written for the searching of an element. If tree data is equal to value or tree is equal to null, then return the root node, that is the tree node, which is having this particular value. Else, if the value is less than the tree data, then you need to traverse to the left subtree, and you are supposed to find the value. Otherwise, you need to traverse to the right subtree and find the value. So this is the way how the searching operation will be performed on binary search tree. Next, we will see the algorithm to insert a value into a binary search tree. It is just like recall the creation of nodes in the single linked list. First, always we'll check whether that list is empty or not. How we'll check the list is empty or not by looking at the head value. If the head is equal to null, then the list is null. In the same way, in the binary search tree, we'll take care of a pointer called root pointer. If the root pointer is null, then we can say the tree is null. So the insertion operation, the pseudocode for the insertion operation is as follows. Insert tree comma value. Step 1. If tree is equal to null, then create a node and assign the value which is going to be inserted into the tree. The starting value which is going to be inserted into the tree is the root value. Now this particular node will become the root value. If a tree is existing, that means if the root value is exist, then some more elements is going to be inserted into the binary search tree. Then you are supposed to check the inserting node is less than the root node or not. If it is inserting node is less than the root node, recursively call the insert function and try to insert this element in the left subtree of the root. Otherwise, you recursively call the insert function to insert the value into the right subtree of the binary search tree. So this is a very simple pseudocode that need to be implemented for creation of the or for the insertion of the elements into the binary search tree. Next, deleting the value from the binary search tree. Deleting the value from the binary search tree is a uh, very should be done very cautiously. The reason is if a node which is having or if a node having multiple children, a single child or multiple child was deleted just like that, then the children will become orphan. So that is the reason the deletion function deletes a node from the binary search tree. However, care should be taken that the properties of binary search tree do not get violated and the nodes are not lost in the process. The deletion of a node involves three cases. Here, three cases are considered for deleting a node from the binary search tree. The first case is the deleting node is a leaf node or not. If the leaf node exists, that means the deleting node is a leaf node, directly we can delete the particular node. And second case is the whether the deleting node consisting of either left child or right child need to be checked. That is what is called case 2. In case 3, a node deletion with both left and right child. That means a node consisting of both children, left and right children. That is case 3. Now we'll see the case 1. Deleting a node that has no children. So for example, deleting the node 78. So how to delete the node? First of all, you need to search for that node. So how to search that node? 78 is compared with the 45. So since 78 is greater than 45, we have to move into the right direction. That is the right subtree of the binary search tree. Now 56 is compared with 78. So 78 is greater than 56. So you have to move to the right hand side. Now 78 is equal to 78. Now the node was found. Now check whether the element or the node that you have observed, for that do this particular node consisting of left child and right child. So if the nodes left is equal to null and right nodes right is also equal to null, then we can confirm that it is a leaf node. Whenever we confirm it is a leaf node, directly you make this particular node as null and free this node so that this node will be removed from the binary search tree and the resultant binary search tree will look like this. Okay, so this is the way how the case 1 will be executed or case 1 will be solved. The case 2 is deleting a node with one child. That means either it may have one child, that is either may be having left child or maybe right child. To handle the deletion, the node's child is said to be the child of the node's parent. That means the node which is going to be deleted, if it is having either left child or right child, then it must be assigned to the parent of the deleting node. Then that node need to be deleted. Now if the node was the left child of its parent, the node's left becomes the left child of the parent. Correspondingly, if the node was the right child of its parent, the node's child becomes the right child of the node's parent. So now here we are supposed to delete a node called 54. In this uh, in this 54 is compared with 45. 54 is greater than 45. We have to move into the right direction, and 54 is less than 56. So we have to move to the left direction of the 56. Now 54 is matched here. Now the 54 is matched here, but we have to check for the condition whether the 54 node 54 left is equal to null or right is equal to null. So, but here left is equal to null, but right is not equal to null. That means it is having the right child. So whenever it is having right child, what we are supposed to do is we need to we need to provide or we need to give this particular node 55 to the we need to attach this node 55 to 54's parent. what is the 54 parent? 56. So to 56, we need to attach this 55 and we need to remove this particular 54. Otherwise, what will happen? If we directly delete the 54, 55 will become orphan. So the reason the single child must be attached to the deleting node's parent and the node must be deleted. This is the second case. The third case is very difficult and should be done very carefully. The reason is the third case is deleting the node with two children. So previously with no children, we have seen the case one. In the case two, deleting a node with only one children, that is either child or right child, we have seen. Now we'll see the deletion of a node with the two children. To handle this case of deletion, replace the node's value with its in-order predecessor, that is largest value in the left subtree, or in-order successor, the smallest value in the right subtree. The deleting node must be the node value of the deleting node must be replaced with either in-order successor or in-order predecessor or in-order successor. So in-order predecessor means the smallest value in the left subtree must be picked up and should be placed in the node which is supposed to be deleted, or the smallest value in the right subtree will be picked up and will be placed in the node value where you are going to delete that particular node. The in-order predecessor or successor can be deleted using any of the above cases. That means either you may use case 1 or case 2 to delete this in-order successor or in-order predecessor. Now, assume that you want to delete a node called 56. Now the 56 is compared with 45. 56 is greater than 45, so we have to move in the right direction. Now 56 becomes the 50. 56 was matched and the node 56 was found. Now we are supposed to check whether the node 56 left is equal to null or and right is equal to null. So 56 left is not null and right is also not null. That means this is a node consisting of both left and right child. So now either you use picking of the in-order predecessor or in-order successor. So here the in-order predecessor is going to be picked up here. That is largest value in the left subtree. That is up to you to choose whether in-order predecessor or in-order successor. That is up to you. Okay. So here, according to the diagram, they have chosen the in-order predecessor to be picked up. The in-order predecessor is the largest element at that is largest value in the left subtree. Largest value, how you will find? That means in the 56 left subtree, we have 54 and 55. In this, what is the largest value? 55. That 55 will be placed here. That is, 55 is placed here. Whenever the 55 is placed, you need to apply deletion of the 55 on the left subtree of the corresponding node, that is 55 here. That means since 56 is replaced with 55 at the left hand side of the 56 node, that is old 56 node. So here left subtree is 54 and 55. Now 55 is compared with 54. So 55 is greater than 54. Now you come to the 55 at the right hand side. Now we are going to check whether this is having left subtree, left child and right child. Since the left and right child is not there, then it will fall under the case 1. Directly this 55 will be deleted. When this 55 is deleted, so obviously the resultant binary search tree will look like this: 55, 54, 55, 54. So 55 is the node which is deleted over here, and 56 is the node that we are supposed to delete, also not present in the binary search tree. Thereby, the binary search tree condition of having the lower values than a node will be at the left subtree, and greater values of than a node will be present at the right subtree. this condition is satisfied in the final diagram or final binary search tree. That means you perform either insertion operation or deletion operation. The binary search tree property should not be violated. So by taking care of this, we are supposed to proceed this binary search tree insertion and deletion operations. This is the algorithm for deletion. This is a pseudocode for the deletion. If tree is equal to null, then nothing to be deleted. If then we are supposed to search for the value to be deleted. If the value is less than the tree data, then move at the left subtree. If value is greater than the tree data, then you move at the right subtree and try to delete it. Else, if tree left and tree right is present, then it is the case 3. Otherwise, case 1 and case 2 will be executed. So here tree left and tree right. That means this tree right, left is not equal to null and tree right is also not equal to null. Then set temp is equal to find largest node at the tree left. So this is what the in order predecessor we are going to identify. So the find largest node means finding the biggest number at the left subtree of the node that is identified. Then tree data is equal to temp data, that is the temp value, that is the node data will be placed, and delete at the left subtree of the deleting node this temp data. That means in this example case it is 55. So again, recursively the same deletion operation will be run, and this particular 55 will be deleted, and finally the resultant binary search tree will be available with the root. So this is the way how the deletion operation in the via pseudocode was represented here. This is in the case 3. Else set temp is equal to tree. If tree left is equal to null and tree right is equal to null, then it is said to be a leaf node. So set tree is equal to null. That is what the value to be deleted is directly is equal to null and free it. Else if tree left not equal to null, that means either it present either left child or right child. In such cases, set tree is equal to tree left. That means to the parent node, we are supposed to place the tree left. That is either left child to be placed to the attached to the parent node of the deleting node, or right child to be attached to the parent of the deleting node. So this is what the pseudocode that is for the deletion of the node. And in the binary trees operation, we have seen the terminologies like height of the binary search tree. Height of the binary search tree is the maximum depth of any node in the tree. So in order to determine the height of the binary search tree, we will calculate the height of the left and right subtrees. Whichever is the highest, whichever is greater, then 1 is added to it, because root is also there. So 1 is added to it, and the resultant value will be the height of the binary search tree. Since height of the right subtree is greater than the height of the left subtree, the height of the tree is height of right subtree plus 1, that is 2 plus 1 is equal to 3. In this case, height of the left subtree is 1 here, height of the right subtree is 2. So the height of right subtree will be considered, height of the right subtree is considered, and plus 1. So thereby you will get 3. So root is at 1, and 78 is at 2, and 80 is at 3. That means it is the height of this particular binary search tree is 3. That means you are supposed to calculate the height at the left hand side, that is left subtree and right subtree. Take the maximum of height of left subtree, comma height of right subtree. Whatever is the maximum you will get, that is the maximum value, plus you need to add the height of the root also. That is reason plus 1 is equal to 2 plus 1 is equal to 3. So this is the height of the height calculation pseudocode. If tree is equal to null, then return 0. Else set left height is equal to height of tree left. Set right height is equal to height of tree right. If left is greater than right height, then return left plus 1. Otherwise, right plus 1. So this is the way how the height calculation will be happened. And next, determine the number of nodes in the binary search tree. Number of nodes, you can go in the in order traversal, that is by visiting the left hand side, by visiting the left node and parent, then right. So recursively perform the in-order traversal and count the number of elements. So to calculate the total number of elements in the node in the binary search tree, we will count the number of nodes in the left subtree and the right subtree plus 1. That is plus 1 means root value. So total number of nodes in the left subtree plus total number of nodes in the right subtree plus 1. So either you may do like this or you may also perform the in-order traversal and count. So thereby you will get how many number of elements that can be that are available in the binary search tree. So if tree is equal to null, according to this, if tree is equal to null, then return 0, else return total nodes of tree left plus total nodes of tree right plus 1. So this is the way this number of nodes will be calculated in the binary search tree. Finding the mirror image of the BST. That means just exactly opposite copy or mirror copy of a binary search tree. Mirror image of a binary search tree is obtained by interchanging the left subtree with the right subtree and right subtree with the left subtree. So left subtree with the right subtree at every node of the tree. For example, given the tree T, the mirror image of T can be obtained as T dash. So 45 is there. Now the left subtree to be copied at the right and 78 is the right subtree value will be copied at left. For 78, 79 will be copied at the, since 79 is at the right hand side, that will be copied to the left side, and 54 is at the left side, that will be copied to the right side. To do this, obviously you are supposed to perform the swapping operation. You may use the swapping operation for performing this. It is just like identifying. It is just like looking like a mirror image. If tree is not equal to null, then mirror image of tree left, mirror image of tree right. So while doing this, we need to place a temporary variable, that is for swapping purpose. A temporary pointer need to be set. For that, we need to assign the temp left to be assigned with temp right, and temp right should be assigned with the temporary variable, which is taken for the swapping purpose. This swapping need to be performed. This is the mirror image. Deleting a BST. To delete or remove the entire binary search tree from the memory, we will first delete the elements in the binary search tree in the left subtree, and then delete the right subtree and delete the root node. So this is the way you will do this deletion of the tree. If tree is not equal to null, then delete tree at the left subtree, left hand side, and delete the tree at the right hand side and free the root node. This is the order we are supposed to follow in order to perform the binary search tree deletion. So I told you in the last lecture the beauty of the binary search tree. Whenever the binary search tree is formed, if you perform the in-order traversal, you will get the elements in the sorted order. And after constructing the binary search tree, if you traverse towards the leftmost node, that is leftmost side, then you will get the smallest element. In the on the binary search tree, if you traverse towards the rightmost node, then you will get the maximum element in the binary search tree. So the basic property of BST states that the smaller value will occur at the left subtree. If the left subtree is null, then the value of the root will be the smallest and compared with the nodes at the right subtree. So that means if a BST does not have the left subtree, then the root itself is the smallest element. So to find the node with the smallest value, we will find the value of the leftmost node of the left subtree. However, if the left subtree is empty, then we will find the value of the root node. The pseudocode for this is find the smallest element of the root, that is the tree. If tree is equal to null or tree left is equal to null, then return tree. So that is null will be returned. Otherwise, return find smallest element of the tree left. So that means you are supposed to traverse till the end of the tree left. Then we need to return the smallest element. So that means this function is called recursively. So tree left, if there exists tree left, again tree left will be called, and if tree left is not equal to null, then again tree left will be called. like that recursively, this tree left operation will be called till the tree left is equal to null. Then the if the tree left is equal to null, or uh, tree left is equal to null, then in such a cases, then return that particular tree left value. So it is the way of traversing the tree left, that is the root left, till left side value is not equal to null, and the last value will be returned. Thereby, you will get the smallest element. The same operation we are supposed to do for the right hand side also. That is, if you want to get the highest value, that is, if you want to find the maximum value in the binary search tree, the basic property of the binary search tree is the smallest values will be at the left hand side and the largest values will be at the right hand side. So that is the reason in this case, if tree is equal to null or tree right is equal to null, then return tree. Else return find the greatest value or largest element, tree right. That means you are supposed to move at the right hand side. That is what the small change you are supposed to do in order to identify the greatest element or largest element in the binary search tree. So this is what the binary search tree and binary search tree operations. The main problem with the binary search tree is the binary search tree is an extraordinary representation for searching operation in the log n time complexity. So log n to the base 2 complexity. How far this log n to the base 2 complexity will be sustained? This log n to the base 2 complexity will be sustained till the binary search tree height is normal. If the binary search tree height is normal, then the log n to the base 2 searching will be performed. But if the height is imbalanced, then what to do? What is the problem with that binary tree? If the height is imbalanced, you cannot achieve the advantage of the binary search tree of searching an element in the log n to the base 2 complexity. So why this particular problem occurs? The problem occurs because of the imbalance in the height. When we will get the imbalance in the height? We will get the imbalance in the height when the elements are almost in the sorted order to be inserted into the binary search tree, or elements are in the descending order, that is to be inserted into the binary search tree. In such cases, you may not get the tree in a proper height. The height will be completely imbalanced. In such cases, you cannot search an element in the binary search tree within log n complexity. Assume that you are supposed to search an element called 12. You are supposed to search an element called 12 in this binary search tree. How many number of nodes are there in this binary search tree? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Total 11 nodes are there in this binary search tree. Now, in order to search 12, how many steps you are supposed to, within how many number of steps this 12 will be identified? First, 12 will be compared with 45. This is the first step. If since 12 is less than 45, we have to move at the left hand side. Now 12 will be compared with 39. Since 12 is less than 39, we have to move at the left hand side of the 39. So here at 45, comparing with 45 is one step, comparing with 39 is second step. Two steps are there. In third step, 12 is compared with the node 12. The searching element 12 is compared with the node 12. So 12 is equal to 12. So here the element was found. That means this is the third step. That means within three searching steps, that is at 45, at 39 and 12, within three searching steps, you have identified the element that is going to be searched. The number of elements here are 11. 11, if you arrange in the 2 power, so it will be around 2 power 3 plus something. So that means log n base complexity is the binary search tree. Log n complexity in the sense, here log 11 is the number of elements to the base 2. It is almost 2 cube plus something. So log 2 to the base 2 will be cancelled. So you will get a 3. That is within 3 steps you have identified this element. Since the height is balanced. Since the height is balanced. Because you look at left subtree height is around 1, 2, 3, 4. And right subtree height is 1, 2, 3. So left subtree height, maximum of left subtree height and the right subtree height, 4 comma 3, 4 plus 1. So the entire tree height is 5. And the right subtree, the height of the left subtree and height of the right subtree is not greater than 1. That is, left subtree height is 4 and right subtree height is 3. 4 minus 3 is 1. So 1 is not a big task because log 1 to the base 2 is not a big step to do. But if the height is completely imbalanced in the sense the left subtree height is maybe greater than the right subtree height. Okay. So in such a cases, the imbalance occurs. Assume that, assume that I'm going along with these elements, I'm going to insert some more elements. What are the some more elements? Assume that I want to insert some more elements such as uh, such as uh, uh, such as 30, comma 31, comma 27, comma 13, 27, comma 26. So these are the elements I want to insert. Now first one is 30, next one is 31, next is 27, next is 26. 30 is compared with 45, which is less than 45. 39, 30 is compared with 39, less than 39. 30 is compared with 12, greater than 12. 30 is compared with 39, 34, which is less than 34. 34, then 30 is less than 32. It is going at the left hand side of 30, 32, right? It will be, now 30 will be like this. 30 may be placed here. Okay, 30 will be placed here. Like that, 31. 31 is 31 is now 31 is now less than 32. So, but greater than 30. So it will be placed at the right hand side of the 30, right? So next one is 27. Where is 27 now? 27, 39, 39, 27 is less than 39. So move at the left hand side. 27 is greater than 12. Move at the right hand side. 27 is less than 34. Move at the left side. 27 is less than 30. Move at the left side. At 30 left side, you will go like this. Now, I want to search for, after inserting these elements, I want to search for the element 30 or 27. So assume that I want to search for 30. 30 means 1, 2, 3, 4, 5, 6 searches I need to do. 6 searches I need to do in order to search the element 30. Thereby, what happened here? We are discussing so far that binary search tree will give us searching time complexity as order of log n to the base 2 time. But here 6 searches we are doing. But there are only previously 11 plus now 4. There are only 4 what you call 15 elements. That means almost you said 16 elements, 2 power 4. But here what we are doing, we are making 1, 2, 3, 4, 5, 6 searches. It is greater than the number of the specified time complexity, that is log n to the base 2. Assume that the number of elements are 16, then means at most in 4 searches you need to identify the element. But here it is taking 6 searches. We are going to take 6 searches to identify the element 30. The main reason for this is the height is imbalanced. The height is imbalanced. Since the height is imbalanced, the binary search tree is not giving the advantage of searching an element with the at most log n to the base 2 complexity. This is what the disadvantage of the binary search tree. Once the binary search tree height is not balanced, that means the here it's not balanced in the sense the height of the left subtree may be greater than the height of the right subtree, or height of the right subtree may be too greater than the height of the left subtree. In such a cases, the height imbalance takes place. Whenever this height imbalance takes place, then it cannot give, that is binary search tree cannot give the searching complexity, or that is the searching of the element with at most log n to the base 2 steps. So that is the reason this binary search tree will be used only till the height binary search tree height is perfectly balanced. So that is the reason in order to take this advantage, there exists a tree, separate tree was developed, which is called AVL tree. This AVL tree is a binary search tree with a height balancing property. This AVL tree will eliminate almost all the problems of the binary search tree of height imbalance. So that is the reason AVL tree is highly preferred for maintaining the perfect searching with the in the form of binary search tree property, or with the help of binary search tree. So tree is a general formation. Binary tree is a condition on the tree having zero or more, zero or at most two children. Binary search tree is a binary tree with additional condition, that is the left hand side values, left subtree values are less than the root value, and the right subtree values will be greater than the root value. And AVL tree is a tree which is a binary search tree with one more condition, that the height balancing property must be satisfied. This height balancing property is calculated as height of left subtree minus height of right subtree should not be greater than 2. So this particular balancing property will be maintained in the AVL trees, and this AVL tree is in detailed description of insertion, deletion operations, and many other operations on the AVL tree will be discussed in the next lecture.